So the purpose of this, I hope, short lecture is to accompany section 10.1 in the lecture notes about check digits. And the idea here is, or the idea of the notes was to give various examples of systems of adding one or more check digits to long numbers, like the numbers used to catalogue books, or bank account numbers, or credit card numbers, and so on. And I recommend you look at the examples in the notes. Perhaps the most interesting one is the LUN algorithm that's used to check most credit card numbers, sometimes called the double alternate method. But I've decided, I wasn't going to give this lecture actually, but I've decided I was trying to check my own IBAN, International Bank Account Number, and I found it harder than I expected. So I've decided to talk about this example, and it's a good example to explain the use of check digits. So I've chosen an example of a UK bank number, international bank account number, and it's a fake number. I got it from my own by modifying a few digits. But this number, which I've written down here, does pass the validation test. If you go online, there are various firms trying to sell you their software, and they will validate IBANs. And this one passes the test, and I want to explain to you why it passes the test and what tests are carried out. So this is a thing which has this long number. It's not really a number because it has alphabetical characters as well, has a total of 22 characters. That's for the UK. Other countries have different numbers of characters. France and Italy have 27 characters in their IBANs, as they're called. So let me just explain what the different parts of this number represent. So obviously the first two characters are the country code. Now the next two are the check digits which we're going to compute. So these don't directly tell you information about the bank account, but they're manufactured from the other remaining 20 characters algorithmically, and I'll explain that later. So these are the check digits of the IBAN. Then obviously we have the name of the bank, which in this case is Lloyds. And then the next 6 digits in the UK system would be the sort code of the bank code, if you like. The 30 probably also tells you it's Lloyds, there's some overkill here. And this will also tell you the location of the bank, in this case in Oxford. And then the remaining numbers are the account number, in this case a sterling current account number, that probably started life with a total of 6 digits, but at some point account numbers were converted to 8 digits, so 00 was added at the front. So those are the parts of the IBAN, and I want to explain now what validation this goes through. So the first part of that is actually what you might call a national validation of this part of the numbers. So this corresponds to the sort code and the account number, and this goes through a separate, simpler validation process that's it's rather difficult to find the details of this, but in the case of it, because the validation depends upon the bank and sometimes the sort code. But in this case, what happens is that it follows the sort of system that is used in the old book number system, ISBN 10, which is in the notes, in which you basically you use mod 11, you check something mod 11, but you have to weight the different numbers here with weights and add up the sum. So what you do here is let's just copy down first of all the characters here. So the characters are, just copy these down, the numbers 30112700126886. And these are weighted by certain coefficients. This sort of system is also explained in more detail in the notes. And it turns out that in this setup, these are weighted by coefficients 0.03298. That's really what Lloyds Bank has chosen. And then there's some weight here that depends actually on this number here, but here it's 0, so we don't care about it. And then the weights just go 7, 6, 5, 4, 3, 2, 1. And we saw such a sequence of, well, in the notes, there's such a sequence of consecutive integers used in the ISBN 10 system. And then you multiply these numbers, the weights, with the account numbers, and then you can add everything up. So 3 times 0 is 0, 3, 2, 18, 56, 0, 0, 6, 10, 24, 24, 16, 6. And you add all those numbers up, and the sum is equal, I think, to 165. And the point is, this is divisible by 11. So this is equal to 0 mod 11. And that fact means that this part of the IBAN has been validated. That's a sort of separate validation of the national sort code and account number. So that's the first step. So if that's not validated, there's no hope that the whole thing will be validated by these online checkers. But I wasn't really meaning to talk about that part of it. I wanted to really explain the check digits, the 2 check digits that we have near the front. So how do you find these check digits? I now want to explain that. And you do that by really 2 steps. First of all, you move this block of 4 characters. You move that to the end, to the right-hand side of the number. So now it's going to finish with GB27. The reason for doing that is that let's pretend we don't actually know that the check digits are 27. We could call the digits X and Y. So if you like, we're trying to find X, Y. And by moving this block to the end, it means that the number finishes X, Y. And it will make it easier for us to determine X, Y. So that's the first step. The second step is to convert the letters from the alphabet into decimal numbers. And that's done by assigning, we want to avoid digits 0 to 9, so we assign to A, we don't have any A's here, but we would assign 10 to A, and then you just add 1 each time. So basically you're taking the letter of the alphabet's normal position, you're adding 9 to it. So B becomes 11, C would be 12, I'll go as far as D because we do have a D here, D would be 13, and so on. We're going to have a Y as well. Well, if you get to the end of the alphabet, Z would be 26 plus 9, 35. So Y is going to be 34. So we do both of those steps. We put the block at the end, first block at the end, and we convert the letters into numbers. So what do we get? We get we're going to start now with the L. Well, L is the 12th letter normally of the alphabet, so we add 9 to that, that's 21. So this L becomes 21, O becomes 24, Y, as I said, becomes 34, D on my little table is 13, and then the rest of it, as before, 30, 11, 27, that's the sort code, 0, 0, 1, 2, 6, 8, 8, 6. Then we've got GB. G is 16, B is 11. And then we have our check digits, which we pretend we don't know, X, Y. So that's the conversion of IBAN. And how do we validate this? Now I'm going to give you the validation rule. But before I do that, let me call this part of this big number, let's call that decimal number finishing 11. Let's call this number n. Okay, so, and let's call the number between 0 and 99 defined by xy, let's call that c. So now the validation equation that we need to be satisfied if this is to be a correct IBAN is simply that we want this whole number, as I've written it on the paper, as a decimal, as a number to base 10, we want this to be congruent to 1 modulo 97. Well, another way of saying that is that since this number really is 100n plus c, we want 100n plus c to be congruent or equal to 1 mod 97. Now, the reason for using 97 is it's almost as big as 99, so it will give us almost 100, little, give us 97 possible check digits, but it's a prime number, and that's important. Now, of course, 100n is the same as 3n mod 97, so our real equation is 3n plus c is congruent to 1 mod 97. So that's the validation equation. Let's now use that to find c in our case. Well, of course, the numbers involved are too big to put on a pocket calculator. There are too many digits involved here. So I use Sage to actually check the remainder mod 97. So what I did therefore is in Sage, I just went to one of the boxes on Keats actually, and you can type anything, remove what's over there and type what you want. So I typed that n is equal to this number, finishing with 1, 1, I should say. And then on the next line, I simply typed the code in Python or Sage for finding remainders, which is n percentage, in this case 97. And the output I got from Sage is that this is 56. So Sage told me that this was answer, if you like, 56. So that's our remainder, 56. So we need to take 3 times, so you can think of n as being equivalent to 56. So 3n, 3 times 56 is 168. So let's write that here. So 3n is therefore equivalent to 168, which, since we're working mod 97, is also equivalent to 71. So we have that 71 plus c is congruent to 1. So c is therefore equivalent to minus 70, which of course is the same thing as plus 27 mod 97. So that's verified, that's explained why in this particular IBAN the check digits are 27. That's how it works. I just want to finish with some remaining comments. So first of all, there's a bit of ambiguity here because x and y give us that they can go from 0 to 99. That's actually 100 possibilities. But in fact, we can only use 97 from this setup. So the convention is, I believe this to be the convention, is that the number c actually is greater than or equal to 2 and less than or equal to 98. Those are the numbers chosen for the check block. But what I mean to say is that the two-digit number XY is slightly abusive notation. If C is less than 10, obviously you need to insert a 0. So XY would run from 02 to 98. So in other words, if you perform this calculation, which I just did, and your remainder comes out to be, say, 1, then you would not put 01, you would put 98. Or if the remainder was 0, you would put 97 as your check digits in the IBAN. The other thing to say is that the fact that 97 is prime, you see our equation here, 3 has an inverse mod 97. We go back to sort of Euclid's algorithm and the extended algorithm. Of course, 3 times 32 is 96, which is minus 1 mod 97. Or another way of saying that is that 3, let's see, 3, well, let me write that down. 3 times 32, that would be minus 1 plus, so this is minus 1 mod 97. So that means that in the equation, if we have this equation, we have that 3n is congruent to 1 minus c. So in other words, we could therefore express n as being equivalent to minus, well, let's say 32 into c minus 1 mod 97. And that enables us, that shows that in fact any check digit in this range, which I've said here, can correspond to a possible value of n. That's the point where we've used the fact that 97 is prime. Okay, now I just want to finish by explaining how all this has to do with binary codes. What's the motivation here for binary codes? Well, what we've done is we've actually taken a very long, what I call message, the message being the bank information. Okay, so if we forget the check digits, the 2 check digits, we had 20 characters, but then we converted 6 letters to numbers. So that gave us a message actually with 26 decimal digits. To which we found the 2 check digits. So we can call this this part I call the message, and this part here I call the check block. It's more than 1 digit because in fact here there were 2 digits. And the idea is this, that the check block can be used to detect certain errors in the message. So the sort of errors that could occur when you're typing in these numbers is you might make a single digit error, or you might transpose when you're typing quickly 2 digits. So you might type 51 instead of 15. It's the equivalent of saying strat when you mean start. Or there are things called twin errors. Instead of typing 55, you might accidentally type 66. And these are the sorts of errors which this having check digits, 1 or more check digits, will detect. But they won't be able to correct the errors unless they know where the errors occurred. If you know that you have single digit errors in 2 positions in your message, then you can use the 2 check digits of the IBAN to correct those errors normally. But otherwise you can't do that. But in binary codes, and incidentally we won't be using decimals anymore, we'll just be using zeros and ones, In binary codes, we'll have the same setup. We'll have a message to transmit, which will consist of a certain string of binary digits. In our exercises, it will be fortunately less than 26, but in fractal situations, it will be much, much larger than 26. We'll have certain strings of zeros and ones, and then we'll have a check block, which will often be as long as the message itself, or perhaps possibly even longer, which is used not just to detect an error, but actually enable us to correct at least one error wherever that occurred. So that's what we'll be doing for the rest of this week.